All right, so to start things out, if you sent me an email Friday or today and I haven't responded, I'm not trying to ignore you. I'm just backlogged. So I'll try to work my way through all the emails I have in my inbox this afternoon. Also, I uploaded the kind of iClicker scores from Friday. So if you're still not seeing it pop up, it looks like maybe there's 2 people it's not working for. Please talk to me. But I think it looks like most people should be uploading everything correctly. I also put this extra smart book. It just kind of walks through some of the topics and ideas we're going to talk about this week. So obviously start talking about some today, but it might kind of help prime you for some of the stuff we're going to talk about later on in the week as well. We have that first Connect and Excel assignment due at the end of the day Wednesday. So if you have any last minute questions on that, some people reach out to me, send me, want me to kind of take a look over what they've already done. I can do it that way. I'm going to stop at my office. I've got office hours 2 to 4 today and Wednesday. I'll be around the building most of the day tomorrow. So if that doesn't work for you, you can shoot me an email. We can probably find a time tomorrow to work as well if you have some last minute questions. Okay. Is there anything else I want to say? Any questions before we jump into material here? Okay. So, I know the other thing I was going to mention. So I uploaded or I re-uploaded the data file we've been working off in class. So you should have everything that you need in there in the in-class file. Like this was just the blank one. And then today, kind of we'll be working off these lecture slides. Okay. So we'll go back here to the beginning. And I think I mentioned we might talk a little more about percentiles today, but I've decided that we're going to talk about something down the road that makes us a little bit irrelevant, and that I don't want to waste or spend any more time on those. I want to kind of try to just solely focus on probability today. Okay? So we're really going to be kind of switching gears a little bit from what we talked about before, although I'll reference things that we've already done. Okay? So examples of probability. What is this term probability? Right? Well, generally when we talk about it, we say things like, well, what are the chances that something occurs? Or what are the odds that this happens after we see some event occur? Or what's the likelihood, right? So all these are really just terms that getting at, we want to make projections about the future. And we want to know, well, what's the underlying probability that something occurs, right? So maybe if I looked at like a data set and I had a bunch of students and their grades, what they got in my class, maybe I see that, I don't know, 10 out of 100 of the students got an A, right? So the probability that a student in this data set got an A would be 10 over 100 or 0.1, right? That's a probability, right? So we've actually done something pretty similar to this already, right? Remember when we had like the vaping data set or whatever, like, well, how many kids first tried an e-cigarette at age 8? Well, how do we turn that frequency into a relative frequency? We divided by the total number of observations. So thinking about these probabilities, they're really the same thing as when we were calculating these relative frequencies, right? So we've got these probabilities. Now we talk a lot in percentages. So today and most of this week, I am going to be talking in probabilities, right? You can always interchange the two. And as we progress through the semester, I think that'll just be a lot more natural. Right, a probability of 0.1, well, usually we would say like, well, there's that 10% chance a student got an A here, right? So we can kind of work back and forth between those, but probabilities are strictly kind of the decimal form, okay? So we got to set this up a little bit before we get too deep into the probabilities, just thinking about, well, what are we truly trying to measure, right? So every probability, there's an underlying experiment, okay? So this experiment is just going to be something that hasn't occurred yet, and we don't know what the outcome is going to be, right? The outcome is uncertain, however I phrase it here. Yeah. So this could be as simple as choosing a student at random from this data set and not knowing, well, yeah, I know they got an A, B, C, D, or F, but I don't know what that outcome is going to be until I actually randomly select one of the students. Right? You might think about this as, it could be as simple as survey data. I might go ask somebody, what's your income level? Well, I know that they could answer with 0, 1, 2, 3, up to whatever millions, but I don't know the actual outcome that I'm going to record when I ask them that question, when I run that experiment. Okay. So we're going to run an experiment. We're going to run it several times. All right. So this isn't going to be like the same as like physics or biology. It could be as simple as a survey question. Right. But we're going to run this experiment several times and then collect all the outcomes that we see. So that's the idea behind what we're doing. Now, once we have all those recorded outcomes, we might be able to turn those into probabilities. Okay. So the outcomes that we record, right, or the experimental outcomes would be any of the possible responses we could get. So for my letter grade example, if I ignore pluses and minuses, right, I could see them respond, or if I choose a student at random from this data set, I could see A, B, C, D, or F. Those are my experimental outcomes. Now, when I only run this experiment one time, I only get one of those outcomes, right? So when I run the experiment and I write down those outcomes, I might have only a sample of all the possible experimental outcomes. We'll call this our sample space. So all the outcomes that we've recorded from running this experiment, that's our sample space. Okay? I'll give an example of how these could differ. So let's say I'm randomly drawing a card from a deck, right? Most of you probably know the cards you could see from a normal deck. How many people have ever heard or played the game called Rook? Okay, good. And nobody in the last section either. I don't know what this says about me, but how many of you heard of euchre? Okay, feelings. I would describe Rook as just like a more complicated version of euchre with a bigger deck, right? And so I don't know, you don't know what Rook cards are. They might not look anything like a normal card deck. In fact, there are things like the Rook card that are in a normal card deck that are in a Rook deck. So until you take this deck of cards from a Rook deck and start drawing them out, right? You run the experiment, you randomly select one card, you see what it is, you then write what card you saw down, right? Maybe you draw 5 cards and you write all those 5 outcomes. That's your sample space. Now you've only drawn 5 out of, to be honest, I forget exactly how many cards in a Rook deck, but there's a bunch, definitely more than 52. You don't know what all the possible outcomes are, right? There is a set of possible experimental outcomes, but until you run this experiment enough times, your sample space, right, your observations might be a smaller subset of that, okay? I guess if you use a regular card deck, like if you didn't know, we kind of, I think most people know ahead of time, like, I know I could see 2 through ace, right? But, you know, if I only draw 3 cards, I'm only going to see 3 of those possible outcomes, right? So if I draw more and more, eventually I'll see every single possible outcome. Okay? And then we're going to have something we call an event, which is just something we define as a subset of this sample space. So if I'm drawing cards from a deck, you know, my event that I've defined is I might only be interested in if I draw a king or an ace, right? That's my event. There's only 2 outcomes in my event, and it's a subset of all the possible experimental outcomes or of my sample space. Okay? So these are kind of like getting smaller and smaller. So like a nice visual is my experimental outcome space is this huge, like every single possible outcome I could see. I can run this experiment, I don't know, a dozen times. I write those outcomes down. I now have my sample space, which may be smaller, right? I might not have seen every single possible outcome. And then the event I define as it's a very specific set of outcomes within that sample space. Okay. Any questions on that? It's making sense so far. Just kind of setting things up here. So we can think of different examples, right? And these are like, I don't say toy examples, but these are kind of just some basic ones to start out with. They obviously get a little more complicated as we move forward. Right? If I flip a coin, my outcomes are I get a heads or tails, right? If I roll a die, unless it's I'm Dungeons and Dragons or whatever, right? I'm a 6-sided die. I'm going to see 1, 2, 3, 4, 5, or 6. Right? Choose a card deck or choose a card from a deck, right? I can see I already mentioned this one, right? Ace through king, right? And here it becomes important. Well, it actually depends on what we're interested in. So the experimental outcome space for drawing a card from a deck is ace through king, unless I'm also worried about the suit, right? And then I get a lot more possible outcomes, right? So sometimes the experimental outcomes are defined as like what we're interested in, the question that we're interested in, right? If I'm just interested in, the probability of getting an ace on the next card flip and I'm playing poker, well, just getting an ace might work for some hands, but for other hands, I might need an ace of spades, right? So it just kind of depends on the question we're trying to answer. And I was thinking here, I need to add in a playoff football game. I think about win or lose, and then playing a soccer game, which I can see win, lose, tie. But we can think of a ton of different types of experiments, but they don't have to be like these complicated things. It could be as simple as like the ones I've given you here. Okay. Any questions up to this point? Shouldn't be too bad. Okay. So I guess the textbook definition, right, is probability is the measure that the likelihood the experimental outcome will occur once I run this experiment, all right, once I carry out this experiment. So the probability of an event will just be the probability of every outcome in that event added up. At least that's how I'll define it for now, right? We run into a slight roadblock with this, but I think we'll get to right at the end of class today. So you can think about it as, okay, what's the probability? And I'll explain this notation a little more here down in a second. Let's say I want to know what's the probability if I roll a 6-sided dice so that I see it come up with a 3, right? So if I roll a 6-sided dice, what's the probability if it's not like, you know, I didn't mess with it, so it's weighted. Probably I see a 3, it should just be 1 out of 6. There's 6 possible outcomes. I'm interested in one of them, right? Well, what's the probability that I see this roll take on a 3 or a 4? Well, the probability I roll a 3 is 1/6. The probability I roll a 4 is 1/6. So if I add those together, that's how I would find the probability of this event. This event includes 2 outcomes, right? So if we want the probability of the event, we simply add up the probability of the outcomes that are in that event. Okay. Any questions there? So in general, the way we write these, I kind of already alluded to it, but like the probability of this event we write with P, parentheses, and then whatever the event is, right? So E is the event. In this case, it was that I saw this roll the dice X become a 3, or that I saw it was a 4. Okay. So if I think about where could this probability lie, what's the lowest probability I could ever see? If I roll a dice, what's the probability I roll a 9? Can't roll a 9. There's 1 through 6, right? So that probability would be 0, right? Can't see something happen like negative times. It just doesn't happen, right? So the lowest the probability we could ever see, just like when we were talking about relative frequencies, the lowest you could ever see would be 0 out of something, so 0. Right? What's the highest probability I could ever see? Not very likely I'll see this, but if it's a guaranteed outcome, if something was a guaranteed outcome, what would you say that the probability it occurs would be? Even if you said 100%, right? That's fine, but we have to remember we're dealing with probabilities. So if it's 100% chance of something occurring, that probability would be 1, right? So we know the probability of this event lies somewhere between 0 and 1. Okay. From there, if we go back to like that vaping data set, and I think about what I was doing with relative frequencies, which I'm now telling you are basically just probabilities. So if I took the probability that somebody first tried, you know, these e-cigarettes or vapes or whatever at age 8, add to that the probability they try to age 9, add to that the probability try to age 10, and I add that up all the way through when it was 18 or 19 was the highest value in our data set, those should have all added up to, remember what we said the relative frequencies need to add up to? 1. Why? Well, because I said, what's the probability that I see any of all the possible outcomes? Well, that's a guarantee, right? I'm guaranteed to see at least one of those ages come up. And so the same idea here, if I'm looking at my probabilities, right, and I add the probability of every single possible outcome up, basically what we were doing before with relative frequencies, they should add up to 1. Okay. Any questions on that before is that clear? Okay. So I've already alluded a little bit to how we get these probabilities, but we're going to have 3 different ways of assigning them, right? So the first one's pretty easy, right? So this will be the classical method. And basically it's when we have these situations where it's kind of like we have to have a little bit of knowledge ahead of time where we know everything's equally as likely. So if everything's equally as likely, when I was rolling a 6-sided dice, I said the probability of any one of those numbers coming up was 1 out of 6. If I flip a coin, what's the probability I get a heads? As a fraction, it would just be 1 over 2, right? 2 possible outcomes. So 1 over 2, or probability of 0.5. But what if I had 100 possible numbers? Like I've got on little pieces of paper, 1 through 100 written down, and then I select one at random, right? Well, what's the probability that the one I selected at random was 23? Well, it would be 1 out of the 100 possible pieces of paper. So really all we're doing there to get our classical probability, if we're assigning them classically, is 1 over n, right? 1 out of, or the possible outcomes I could see, okay? So if I think about instead, Oh, sorry, this is my summary slide. Yeah, so we have three different ways. I already jumped into the first one, right? We've got three: classical, empirical, subjective, right? So classical was the one I just kind of described. Now, what if I think about flipping a coin twice, right? What are all the possible outcomes I could see there, right? Well, I could see a heads, then a tails, heads, then a heads, tails, then a heads, two tails in a row. So if I'm interested in the probability that if I flip a coin twice, that I see it come up heads both times, that probability should be what? How many possible outcomes do I have when I run this experiment of flipping a coin twice? 4. So the probability of any one of these being the outcomes that I see should just be 1 over 4, right? Number of possible outcomes that I have. Okay. So not trying to complicate it too much, right? However many outcomes we have, if they're all equally as likely, then probably each one occurs just 1 over how many possible outcomes I have. Okay. Questions on that before we keep moving? That one shouldn't be too bad. Now this is like very specific situations. More generally, we're going to have to use the empirical method, right? So we've already really done this when we were building that frequency distribution for the age they first tried e-cigarette or whatever example. But I'll give you a slightly different context. So let's say I'm like interested in the local restaurant demand, and I am surveying Ball State students and trying to figure out what's the most popular type of food or cuisine, right? So I go around and ask 60 students at random, right? Each student I'm asking, that's the experiment. I then get a certain response. I record it. That's the outcome, right? So I record all this and I see that 15 of them responded with that Mexican cuisine is their favorite, or Mexican food's their favorite. So how will I assign the probability for the future if I select a person at random from Ball State students? What's the probability they respond with Mexican food as their favorite? Well, based off of the data I've already recorded or the experiments I've already run, 15 out of 60, right? Or 0.25 is a probability, or 25%. Okay. So all I'm doing there is recording, just like with the example I had, like 10 students get an A. I'm just running this experiment, recording the outcomes, and then getting the frequency of each outcome divided by the total number of observations. All I'm doing with the empirical method is essentially creating these relative frequencies. And those are the probabilities I'm assigning to each one of these possible outcomes. Okay. Any questions on this? So what's probably really useful if I'm using the empirical method? Running this experiment more and more often, right? If I only have 10 people asked here, the probabilities I'm assigning might be really off from like the general population as a whole, right? Maybe I go out and ask 10 people. This is probably not very likely, but all 10 of them say, I don't know, even if you ask their favorite food, they all respond with hamburgers or something like that, right? Well, I probably just have a really skewed 10 people. If I ask 1,000 people, I doubt that I get all 1,000 to respond with that hamburgers are their favorite type of food, right? So we want to try to run these experiments a really high number of times, right? Or get as many of these recorded outcome responses as we can. Okay. The last one, I had someone ask the last class, like, the empirical method is great, right? I'm trying to make projections based off of real data that I've recorded. Well, what if that data is old, right? It might not be very relevant to the current probabilities, right? Maybe those probabilities have changed, okay? And so in some situations, we have to use the subjective method, which is that, well, look, we can look at not recorded outcomes, but we can look at other data, right, to make a good inference about what the probability should be. So I'll give you an example. Let's say we have, a company trying to hire a CEO. We've got 4 candidates. Well, I probably don't want to use the classical method, right? Every single one of these has the same likelihood of getting the job, because maybe I start looking at the resume and, Andy's only ever worked, as a fast food line cook, and then Rankin's, run 3 companies already, right? And so I have all this other information that, I haven't run this exact experiment before. Like I haven't had these 4 same people apply for the CEO position, but based off of their resumes, I can come up with a good idea about who's more likely to get this position. So, some industry expert or whatever kind of looks through the resumes and said, well, here's kind of what I would think the probabilities would be. Now, obviously, this is subjective, right? There's a lot of subjectivity in it. But hopefully, if we're using the subjective method, we're also trying to be a little objective, using information from the resume. So it's not completely subjective, but it is in the sense of like, we're not actually seeing previous outcomes of this specific experiment, right? We might see other CEO positions where we had 4 similar candidates, and we might use that to make projections, but we don't actually have this exact experiment with the same 4 candidates for the same position. Okay. Does that make sense? Any questions on that? So that way might seem a little hokey. 90+% of the time, we're probably going to be able to use the empirical method. And then I always thought, after I explain that, like, I feel like it's like, okay, so we're just making numbers up. So welcome to probability statistics class where the numbers are made up, or wait, everything is made up and numbers don't matter. You guys haven't watched Whose Lines anyways. I'm just doing my public service announcement. Go YouTube some of the old clips. They're hilarious. They still hold up. Okay. So that kind of gives us our basis, right? We've been talking about probability. We kind of have some of these basic concepts in mind. I'm going to complicate it a little bit, or I shouldn't say complicate. We're just going to think about it in a slightly different way. And I'm going to point some things out later on. I'm just going to reference what we do, but I'll end up having to erase it. So it might be good to take notes as I'm kind of working through this. So let's say I've got some event A, right? So I'm going to use the experiment of just rolling a dice. It's an easy 1, 2, 3, 4, 5, 6 are my possible experimental outcomes. I then define this event A as seeing one of these possible outcomes, right? 2, 3, or 4, right? Those are my outcomes that are in my event A that I've defined, okay? And you don't have to, I'm not going to use set theory probably after today, but these squiggly lines, I'm just kind of using that to say like, here's the outcomes that are in this event, okay? If I want to find the complement of an event, I'm going to write this as, well, whatever event I'm interested in with a superscript C, right? Or like looks like it's to the power of C, right? All this means is the complement of an event is everything not in that event. So A complement, another way of saying that is everything not in A, okay? So here, what would my outcomes be that are in A complement? So I'm rolling a 6-sided dice. The only outcomes that are not in A would be
1, 5, and 6.
Yeah, 1, 5, and 6. Those are the only outcomes I could see rolling this dice that would not be in event A. Okay. What if I had event B defined as 4, 5, and 6? What would my event B complement be? It's every outcome that's not in B. So that would just be
1, 3, and 2.
Yeah, 1, 2, and 3. All right. And that makes a good point. You said 1, 3, and 2. It doesn't matter which order I say them in, right? I'm just writing it to, in order just to make a little, but yeah, I'm just concerned with what those outcomes are. Okay. So that's how we identify the complement. And we'll use this kind of later on. I'll give you some better visuals of this, but for now, we'll kind of leave it there. What if I then wanted the union of 2 events, right? So this kind of set symbol that looks like a U, we'll say that's the union of 2 events, or the way that we might say this in our speech is it in event A or in event B? So it can be in either one, okay? So if I'm thinking about every possible outcome here that's in event A or in B, what would those outcomes be? Well, I can see 2, 3, 4. 4 I already wrote down, or I could see 5 or 6. Right? Those are all the possible outcomes that are in either of those events, right? Some of them are in event A, but not in B. Some of them are in B, but not in A, and some of them are in both. We don't care. As long as it's in one of them, it counts towards the union. Okay. Any questions on that one? Push this a little bit further here. We won't do this a ton, but what if I wanted the complement of the union of A and B? So what outcomes are not in the union of A and B? Yeah, the only outcome here is 1, right? So we can start to do complements of like intersections or complements of, sorry, I haven't told you about intersections yet. We knew the complements of unions, or the next thing we're going to talk about, we can do complements of intersections. So the intersection of two events, we write with kind of this upside down U, right? So this is the intersection of two events, or we can think about this as, is it in A and in B, or is it in both of these? Some people say that it's easy to remember the intersection. You've got this thing, if you draw a line, it looks like an A, so this is A and B, right? However you remember it, you could just memorize it, but that's, I don't know, some people say that helps. So the intersection of two events, or is it in A and is it in B? What are the outcomes that are in both A and B here? What outcome is in both of them? Four, right? That's the only outcome that's in both, right? 5 and 6 are in B, but they're not in A. 2 and 3 are in A, but they're not in B. I want only the outcomes that are in both of those two events, right? In A and in B. So here, my intersection would just be 4, that one outcome, okay? Any questions on that before we keep moving? I've only seen this one example, but I'll just allude to something because it maybe helps as we kind of talk about things down the road. You'll notice the intersection of two events is always going to be in the union, right? Because if I have an outcome that's in A and it's in B, well, then it's in either one of them as well, right? It has to be in them to be, to be in the intersection. So our intersection will always be a part of our union, okay? Any other questions before we keep moving here? All right, so the next thing I'll kind of briefly introduce. We will not really get to this in depth until next class. But I just want to describe what the notation means and kind of set up the ideals when we get to it. I think it'll make the discussion a little easier. So the way that we read this vertical line is this is like conditional, right? Or we sometimes call like given that whatever's on the right-hand side of the line has occurred, or conditioned on whatever event is on the right-hand side of the line has occurred, what's the probability that A has occurred? Right? So I'll give you just a setup of why this could matter if we eventually, here we're just thinking about the outcomes, but we could translate that into probabilities. Maybe event A is that I slip and fall walking into the building, right? Across every single day, that probability is relatively low, right? I don't think I've done it yet, so it's pretty low. However, if you give me that event B has occurred, then it asks me what's the probability of A. Well, what if event B is that it's like freezing rain outside? Well, given that I know there's freezing rain outside, the probability that slip and fall coming into the building goes up a lot, right? So having this additional information, given or conditioned on that something has occurred, having this additional piece of information, I could update the probability of different events occurring. Okay? So that's eventually where we're going to get to with these conditional probabilities. For now, kind of the way we read them is we don't want to know what are the outcomes in this event, or what's the probability we see this event, given that the event on the right has occurred, right? So that's on the right-hand side of that line, that's what we know has occurred. So some nice visuals of this. I occasionally steal things from the book. This is just a nice, easy, kind of quick way to put everything up there. So if I wanted to use Venn diagrams, how many of you have seen those used somewhere in the past? Pretty good amount. So those rectangles are going to represent every single possible outcome we could see. So what did I say earlier? If we add up the probability of every possible outcome, those should add up to 1. So you can think of it like the area of this space is 1, right? That rectangle. Within that, we're just going to use circles to represent the events we're talking about. So here, and actually next class, I'll probably even use like rectangles occasionally because I think it actually can help make it a little bit more sense. But here, everything that's in circle A, that kind of represents to us the probability of A. Everything in circle B, that's the probability of B. Every single thing or outcome that's in both, right? These are outcomes that are in both circle B and in A. That represents my intersection, right? A and B. Every outcome in A and B. If I want the union of two events, well, that's in anything that's in circle A, or it's in B. It can be in both, right? It can be in the intersection, but the union of two events is simply anything that's in either one of these two events. That's kind of how we'll visually represent these things. Questions on that before we keep going? All right. So we're going to have a better way of showing this. I shouldn't say a better way. Just strictly numerical way of writing out these probabilities and thinking about the unions and the intersections. So the first thing that we're going to kind of break down are these contingency tables. Okay. For right now, I'm keeping them very general. I've got A complement, event B complement. We're going to like work through some examples eventually to see how we can take data and build a contingency table. For now, like these probabilities are just being given to us, right? Eventually later on this week, we'll be able to see how from data I can come up with these contingency tables for different events, right? I think the one I might bring in the class is looking at like average weekly earnings being above or below a certain amount and like the percent of that industry that's unionized, right? And so we can give these specific names, but for today, we'll just keep it general, okay? So the way we read these are these top four left cells all represent the probability of the intersection of the row and column head. So here, the probability of A and B is 0.4. The probability of A complement and B complement is 0.3. Right? So those top four left cells all represent intersections. The total column and row, right, represent the probability of the events themselves. So for instance, what's the probability of event A? I go over to my total column of 0.6. What's the probability of B complement? I go down to my total, which is 0.5. So we've got our totals, the probability of the events themselves, and then our top four left cells, the probability of these intersections. Okay. Any questions on that before we keep moving? Just setting things up. So another way, if I left off those total columns that you could reproduce them, is if I add across the rows, like let's say that total column and row wasn't up here. If I add across the rows, 0.4 plus 0.2, notice that gives me my total of 0.6. If I add down the columns, 0.2 plus 0.3, that would give me my 0.5. Right? So I can actually recreate those totals if they don't exist. All right, so I can add down the columns or across the rows to reproduce those totals. So why does that work? So use kind of the entire experimental outcome space. Got circle A here, circle B here. Okay. If I'm just interested in the probability of A, right? So I'm just interested in this circle. I'm going to break it down into two components. So here's one of the components. Here's the second component, right? If I add those two spaces together, that is all of A, right? So let's think about what this shaded black area is first. That's going to be every single outcome that's in event A, but notice it would be outside of B or not in B. Well, what do we call not in B? So this is the probability I'm in A, and I'm in B complement, right? Or I'm not in B. Okay. Is that kind of clear? So this is every outcome that's in circle A, right? We stop because it's not in B, right? So it's the intersection of those two things. Okay. The green space represents what? The probability that I'm in circle A, but I'm also in circle B, or the probability that I'm in A and B. Right? Well, now if I add those two things together, I filled out the entire circle of A. Well, notice the probability of A and B right here, plus the probability of A and B complement is right here. Adding those two things together is just giving me the probability of A. Right? That's why that works, right? It's not just some weird rule. Like it works because I think I told the last class the example was what if I was interested in the probability, like A was that somebody makes more than $50,000, right? Well, if I took the probability that they make more than $50,000 and are under the age of 50, and I add to that the probability that they make more than 50,000 and are 50 or older, Well, that covers every single aged person who's making more than $50,000. So by looking at the intersection of A with an event B, and then the intersection of A with its B's complement, that covers every single other possible outcome for that second event. So that should just give me the probability of A, right? And I can do this the other way as well, right? If I wanted to break this down, I think I had someone ask last class, what if instead I was interested in the probability of B? Well, here I know it's 0.5, right? Everything in this blue shaded area would be what? Everything that's in event B, but it's outside of event A, or everything that's in B and not in A, right? And then I would add to that, right? Everything that's in both of them, that would fill out the entire circle of B. So notice I would take the probability of A and B plus the probability of B and A complement. Those should add up to just the probability of B, and that would match up exactly with what we have up here. So some of this stuff that I'll be doing with the Venn diagrams, I'll try to keep it less dependent on this next class, but different colors might help if you're kind of following along, taking notes. I'll try to start drawing like vertical and horizontal lines, even if I use different colors kind of moving forward. That way, if you're kind of trying to mimic the notes, you'll kind of have vertical and horizontal as opposed to different colors. Okay. Any questions on that before we keep going here? Okay, so I've already talked about how we identify those intersections. Those are those top 4 left cells, right? The totals we could reproduce by adding across the rows or down the columns. So hopefully these next few questions shouldn't be too bad, right? And I'm aware I did not spell question correctly and I forgot to change it before I started class. So this is not Quesiton 1, it's question 1. So if this is going, maybe I think it closed out my iClicker app. Must have accidentally hit the X button instead of start. Oh, it says it's still running. Let's see. Why is it not showing? All right, let's see if this helps. All right, there we go. All right, so I'll get this pulled up and I'll give you a little bit of time to work on this and we'll talk together. So, how is this in progress? All right, let's try this one more time. Okay. So, if I gave you this contingency table, instead of A and A complement, B and B complement, I've set these up as R1, R2. It's still the R2 is the complement of R1. This is giving them different names. In practice, we'll do things like give them names of making more than $50,000. So I leave out that total of X, right? So that represents the probability of C1, right? Using the other information that you're given, you should be able to find what X is or what the probability of C1 is. So I'll give you 30, 45 seconds for this. Shouldn't be too bad if we were following along with what I was just saying, right? I kind of mentioned what those top 4 left cells represent, how we reproduce those total columns. I'm asking you for one of the total cells, so the probability of just C1. All right. If you haven't gotten a response in, take your best guess here. All right, I'm going to close it out. So we got 27 of us here. So what should this answer be? Yeah, how did you come up with that? Yeah, right. I said one way of thinking about this, we can break it down into like the components, but those components are already things that are in our contingency table. So adding across the rows, right? 0.3 plus 0.1 will give us 0.4, or down the columns, we'll reproduce those total amounts. So what? 0.25 plus 0.3 or 0.55 there. Okay. Now, hopefully, if we were paying attention, this one's also just a real easy one, but it gives me an idea about how closely we are paying attention. Let's say here I'm giving you all of the values, but I want you to identify the intersection of two things. So here I just want you to identify the intersection of event R1 and C2, right? The intersection of R1 and C2. Okay. So I'll give you about 30 seconds to look at this, kind of decipher which one you think that's going to be. Right? Remember, I mentioned something about the top 4 left cells, and then we've already kind of went through how we reproduce those totals. So I want the intersection of those two events. What's that probability? I think you got everybody in here, but if you haven't kind of gotten a response, and take your best guess here, you had 27 before as well. Hopefully, I'm afraid to look at that, but what should the response be? Yeah. So I said those top 4 left cells all represent the intersections of the row and column head. So it's as simple as R1 intersected with or and C2, that probability is 0.35. Okay. So we need to be able to identify and grab these intersections because we're going to just kind of complicate it moving forward, right? We're going to have to actually use these to do, a next level of analysis, okay? So hopefully those aren't too bad. Now, when we're talking about those intersections, or eventually we're talking about unions, basically one thing to point out here, we'll start going through some probability laws. The order doesn't matter. Saying the probability of A and B or B and A, I'm still talking about the same thing, right? What's the probability somebody makes over $50,000 and is older than age 50? What's the probability someone is over the age of 50 and makes more than $50,000? So they're the exact same scenarios, right? So the ordering doesn't matter. And the same applies to the union. Doesn't matter in which order we say them, we're still talking about the same space, right? The union is still just the entire white space here. It doesn't matter if I say A or B or A, okay? And then I don't know, throwing this meme in, right? We're thinking about, we have intersections, sometimes they're small. We can actually end up in situations where there is no intersection. And that's going to make our next law a little bit easier sometimes. So I don't know if we'll quite get to when there is no intersection, but if there is, we have a slight problem, right? So let's start off with this rule, and then we'll kind of jump into where we see the problem exists when we want to look at the union. So the complement rule, I don't think this is too bad, right? If we have this space where I've got some event A, and if I think about everything that's not an A, well, that's just A complement, right? So if I take the probability of A, and I add to that the probability that I'm in A complement, that should fill up my entire experimental outcome space. So those two things should add up to 1. I just rearrange this a little bit, right? Move the probability of A to the other side. And I've got the fact that if I'm ever interested in the probability of the complement, that's just 1 minus the probability of the event. Okay. Someone shouldn't be too bad, right? In fact, I had someone last class kind of anticipate this. And instead of adding down the columns or across the rows, it's like, let's say I left these out. How could you come up with X? Well, if I took the probability of C1, and I'm saying C2 is its complement, these two totals should add up to 1. So how would I find X here? 1 minus 0.45. Right? So there are multiple ways depending on what I leave out there. But that would be kind of the using the complement rule. Any questions on that? Shouldn't be too bad. So we'll exploit this a lot. In fact, we'll get so comfortable with it, I think at some point, like I probably won't even explicitly say, we'll almost like, I won't have to explicitly say we're using it. It'll just be a tool that we use quite a bit, right? So here we got a problem. If we want to find the union of two events, we might think it's as simple as adding up the probability of each event. There's just one problem. If I want the union of A and B, if I take the probability of A and I add to that the probability of B, I double counted everything that was involved, right? So if I double counted it, then I'm going to subtract it out once to make sure I only counted it one time. So to find the union of two events, if I take everything that's in circle A, I add to that everything that's in circle B, and then subtract out what's in both, or the intersection, right? Subtract out what I double counted, I'll be left with the actual union. So I'll relate this to what we were talking about earlier to kind of give you an example. And this is where got some of them up here so we can kind of remember what they were. But here, my event A was what? Saying 2, 3, and 4. So if I roll the dice, what's the probability I see A? It's 3 out of 6 possible numbers. So probability was 1/2 or 0.5, right? If I simply thought, okay, what's the probability I see A or B, and I just added up the probability of both of those, well, notice there's 3 outcomes in event B. So I'd add those up and I'd say, oh, okay, yeah, the union of A and B here, or the probability I'm in A or B, is just 1. Well, we know that's not true because if we go back and I had the union of those two events, we said the union was 2, 3, 4, 5, and 6. So what should be the probability of the union of those two events? It's 5 out of the possible 6 outcomes. So the probability of the union should be 5/6. So I just add the probability of both events up, I don't get the correct answer. But notice, what did I do when I just simply added those up? I double counted the intersection, the one outcome that was in both. So if I subtract that out one time, hopefully if this rule is right, I'll get the correct probability. Well, what's the probability if I roll a dice, I roll a 4? Get out sooner if you answer me. 1/6, right? So I subtract out what I double counted, that value of 4 that was in both, and now notice, okay, now I'm getting the correct probability for the union, right? So I think you can kind of see it play out with these numbers a little bit, but the idea is like, if I take everything that's in event A, add to that everything that's in event B, I double count what's in between. So I need to subtract out that probability. Now I've only counted it one time. And I'll break this down in a slightly different way next class, so we can have a different way of thinking about the union. In fact, the different way of thinking about the union helps when we're using the contingency table. But for now, I just want to make sure we're kind of grasping this idea that we double count what's in the middle, so we want to make sure we don't do that. Okay? So we'll pick up here next class. Probably do a little bit of Excel work on Wednesday, looking at how we can build these contingency tables. Other than that, see you guys on Wednesday.